everyone, and welcome to the Volta Foundation webinar series where battery industry experts delve into trending topics. Today, we have a special program lined up with special thanks to the team at PDF Solutions and their amazing industry guests who are here to discuss how to solve cell manufacturing challenges with advanced analytics and inspection. My name is Myra, and I'm the Director of Member Success at Volta Foundation. Thanks for everyone for joining in today. Great topic. I love it. If this is your first time joining a Volta Foundation program, welcome officially to the largest network of battery professionals globally. Our webinar series is one of about 15 programs organized by Volta Foundation, which is a nonprofit organization dedicated to supporting the growth of the battery industry. We produce industry-leading publications like the annual battery report, which was just launched digitally earlier this month, Battery Bits, This Week in Batteries. We host over 50 in-person and virtual events throughout the year, as well as host the largest virtual battery career fair event within the industry. Little side note and little plug for Battery Career Fair. If you're looking for your next challenge, or if you're looking to hire top industry talent, our next program is on April 3rd. With so much in motion, I'm proud to share that everything we do is open access and centered on helping companies and professionals like you connect, collaborate, and advance your business and career. All right. In addition to today's program, like I said, lots in motion at Volta Foundation. Be sure to check out Battery Street, which is Volta Foundation's Slack channel. View past programs on Volta Foundation's YouTube channel. Subscribe to our newsletters on LinkedIn. And be sure to register and join us for upcoming events throughout the year. All right, now that everyone is an expert on Volta Foundation and what's happening, let's chat logistics. For the audience, if you have any questions throughout the program, please enter them into the Zoom chat, and the presenting team will answer as many as possible following the presentation during the Q&A. Find them on LinkedIn too if you have some more questions. If it's platform related, I'll be in the background. Other Volta Foundation staff will be in the background to help answer any questions. All right, and additionally, just a little plug, the PDF Solutions team and the panelists have some really fun polls. So you'll see these pop up throughout the program. So don't be alarmed, nothing's happening. We just encourage you to engage and share your thoughts and feedback and comments with the presenters today. All right, Nika, off to you. Thank you, everyone. Excited for the discussion.
Thank you very much, Myra. Hi, everyone. I'm Nika, and I'm a technical product manager specifically for battery solutions at PDF Solutions. And I'm so excited to moderate this webinar. We have quite a dynamic agenda lined up. I'll very quickly do an introduction about our company and then right away dive into our incredible panel with industry leaders from across the supply chain. We have Selena here, Hailong, Kenzo, and Michael Yu. So let's get started. So PDF provides big data analytics for the semiconductor and electronics industries. And for anyone that's curious, it does not stand for the Adobe document type, but it stands for the probability density function. And that's because the company was founded out of Carnegie Mellon University in 1991 by a lot of very, very smart people. We are blessed to have hundreds of PhDs and very technically talented staff that have issued over 200 patents. We're a publicly traded company and have offices with our engineers working directly with fabs and factories all over the world. To give you an idea of PDF's success in improving yield and helping fab scale, let's look at some of our semiconductor statistics. So over 40,000 process and test tools are managed by our software worldwide. 18 out of 20 semiconductor companies use PDF products, and all the top 6 foundries run on our technology. And very quickly, so we do a lot across different industries, but specifically for battery, I wanted to give you an example, an idea of our overall platform. So here's a very complicated diagram that I'll break down. So we believe that advanced data analytics is the key to solving a lot of challenges manufacturers face in terms of yield, scrap, and ramp up. And essentially, we work in three layers. The top layer that you see is observe. So this is where we collect data from equipment, inspection systems, etc. And in this step, we also provide our high-resolution electrode inspection system, which Peter Koska, the Director of Battery Solutions, will later present at the end of the panel. Then all of this data feeds into a data lake where we clean the data, extract key indicators, and align the data. So you're able to track as the cell moves from electrode manufacturing all the way to cell assembly and end of line. And all of this allows us to create custom software applications for manufacturers where we analyze the data, apply AI to it, which we will discuss during the panel. AI is a really big topic. You might have seen it in the battery report mentioned as well many times. And all of this helps to provide things as simple as a live yield and fault detection and classification dashboard for manufacturers to very complicated applications such as predicting defects early in production and predicting, for example, when equipment needs to be maintenance ahead of time. And because of our process control software modules, we're of course able to create actionable alarms for manufacturers and then communicate directly with equipment or any other software such as an MES. So we work to scale semiconductor fabs in this way, leading them to not only make full use of their data, but to have a robust database, the right sensors, and the right data infrastructure in order to scale fast and improve yield. Because PDF truly believes that data and analytics is at the heart of accelerating R&D, creating really high quality products and scaling production. And we have a very strong consulting background, which has remained in the way we work. So we work directly with our customers to help them solve key yield or quality issues using this enormous suite of tools that we've developed over the years. So that's super quick about PDF. Of course, we're happy to answer questions later if you have any regarding any of these layers or the products that we offer. So I'm not going to keep anyone waiting any longer. Let's get to the exciting part, our incredible panel. So we have an exceptional panel today, bringing together expertise from semiconductor industry and from panelists that have worked to scale up gigafactories at companies like Tesla, Panasonic, Lyten, Molicel, and more. So today we'll be discussing the largest problems in scaling up cell manufacturing and quality, and the role analytics, AI, and advanced inspection play in helping solve these issues. So to start us off, I'd like you all to answer this first poll to help us with our discussion. So Myra, if you could pull the poll up and we can all see it live. So what do you envision data analytics will help you with in manufacturing? Is it yield improvement and quality control? Is it faster scale up, workforce efficiency, or something else? All right, seeing the numbers go live.
Oh, almost 10% say other. I'm curious what that other might be.
Yes, and if you said other, please feel free to put a question in the Q&A and maybe we can discuss it later during the panel if it's something else. All right, wonderful. So hopefully everyone can see the results, but it looks like we had a very good guess as to what the top answers are going to be. We have a very nice distribution scaling down. So we have yield improvement, quality control at 80%, faster scale up at 50, workforce efficiency at around 35, and then other at around 10%. So panelists, I hope this can guide you in our very first question that I'd like you to answer. So to start us off, I'd love for each one of you to introduce yourself, share a little bit about your background, although I'm sure most of the audience knows already what you do. And while you do this, I'd love for you to answer this first question. So from your perspective, what is the most persistent challenge in scaling high yield battery manufacturing today? So Kenzo, maybe we'll start with you.
Sure. Thank you for having me. So yeah, I'm Kenzo. I'm now in my 30th year in lithium-ion battery industry. Still trying to figure out the right lane I should be in. but I've been part of cell OEMs, trying to make cells at scale. I've been on the customer side, buying cells. So I got to visit gigafactories and audit some facilities. Currently, I'm a consultant, and I sit on a few advisory boards for the industry. So yeah, thank you for having me.
Thank you for being here. So would you like to start us off, Kenzo? What is the most persistent challenge in scaling high yield battery manufacturing today, according to you?
Sure. I think historically it has always been electrode manufacturing. I think it still is, and I think it always will be, as far as the sort of the big segments of cell manufacturing. And in electrode manufacturing, it's if you get the slurry right, it kind of it can manifest itself in poor adhesion and cohesion in the coating, and that just causes problems down the line, whether you're winding or slitting or stacking, and all those and sort of subsequent processes. So for sure, for me, it's electrode manufacturing.
Thank you, thank you. Hai Long, I know we've talked about this a little bit as well in terms of the challenges in electrode manufacturing. So maybe please introduce yourself and you can elaborate on that one.
Sounds good. Hi, everyone. My name is Hai Long. I'm a co-founder and CEO of VTA Technology. We're headquartered in Singapore. So we have roughly 40 members, and the core team members have decades of experience in the battery manufacturing space. We build factory in the US, Japan, China. So currently we're providing the manufacturing scale up service and also digital solutions for ramp up and operation efficiency improvement. So a great pleasure to be here and share our learnings. So my view on this is having a good methodology to really scale up from the product design to pilot and to manufacturing. And one of the key points is to have a robust process that allows the cell to be made within the equipment tolerance and capabilities. And Electrode is one of the most challenging areas for this. For example, everybody wants a thick electrode, right, for high energy cell. But when you increase the thickness of the electrode, it's getting harder to coat, and then you have those edge profile that's really hard to manage. And when you have a thicker coating, and during the calating process, you have a bigger elongation, sometimes cause foil breaks. So all these things are related to your product design, how you scale up, and your machine capability. So having a good balance between all these different aspects is a key challenge.
Thank you, Hai Long. Yeah, process control is definitely one of the largest issues in battery manufacturing. So a fun fact for everyone, Selena and Hai Long work together in Panasonic, so I'm sure they share similar views about challenges in scaling up production. So Selena, over to you. Do you agree with what has been said, and do you have anything else to add?
Thanks, Nika. So hi, I'm Selena. I've been working in battery industry for about 25 years, and I started in failure analysis at Exponent and early cell manufacturing, and really have spent a lot of time in factories since the 2000s, in large scale factories, and then some startups as well. Hai Long and I did work together at Panasonic. Kenzo and I worked together at Tesla. So the three of us are good friends. I agree with both what Kenzo and Hai Long have said about electrode making, because if you mess that up, nothing else will be good in your factory. But I would say that maybe more fundamental challenge that you run into when you're trying to scale large scale battery manufacturing is the daunting nature of the CapEx requirements that you've got, right? These factories are so CapEx intensive. They're so big, and everyone has, really big ambitions. And then, you're talking to your boss and, you're like, well, the factory's going to cost X billion dollars, right? And people look at that and they're like, billions with a B. And you're like, yeah, it's great. And the thing that does is it has impacts on how you think about that factory and it creates certain temptations that are really bad too, right? So, the first thing that happens after you say, well, this is roughly what it's going to cost. Everyone says, well, you got to bring the cost down, right? How do you make this more efficient, cheaper? And people have temptations to start cutting things, right? So maybe we don't need all those inline inspection systems, right? That is so common for people to look at, or they look at this and they say, well, okay, we can't afford a lot of extra tools, right? So bare minimum number of tools. And what does that mean? That means that when you actually get the factory built, right, you are really tight on all the capabilities of your equipment. So, it becomes real obvious that you don't have a lot of spare coding capacity. You may have built in some. I sure hope you built in some, because if you don't have spare coding capacity, you'll have other problems. But you don't have as much as you would like. And it's not a simple matter of, oh, let me just bring in an extra tool, because these tools are also just big. The lead times are long, right? So you got this big CapEx bill at the front end. It drives people to really try to minimize their costs. And there's that tendency to say, well, I don't need this, or, that coating's supposed to be perfect, right? The manufacturer told us that the coater was going to be great. I, I don't need all that extra inspection, all that extra data coming through. And why would I invest in those systems when I've invested so much in the tooling? So you can end up with some decisions that really hamstring the production team later on. So I kind of view that as like a fundamental challenge that permeates the rest of the the facility. Um, and and the first place you see it, of course, is in electrode manufacturing, because it's hard. People are like, how hard could it look? It looks so stately and lovely. You go to a factory, you see these roll-to-roll processes, it's all rolling so nicely. And yet all these subtle things, as Hai Long explained, it changes everything. And if you mess it up, nothing else works well.
Thank you, Selena. And what ends up happening is if you cut costs on these important things, such as inspection and analytics, you're going to end up paying for it later down the line, as you said. So what I'm getting from this discussion is obviously battery manufacturing is super complicated. There are so many different variables going on at once. And that's kind of why we're here today, to discuss how analytics and AI and inspection can help deal with these issues. So now I'd like to pass it over to Michael, who's been in the analytics industry for many, many years, and he's seen fab scale, and now he's been in gigafactories. So Michael, what's your perspective on all of this?
Hi, everybody. I'm Michael. I'm leading advanced research at PDF. So my background is a little bit different. My background is actually in semiconductor. So I'm a relatively newbie compared with, all the experts here in terms of battery. The reason PDF got into battery space is because the couple of years ago, many leading cell manufacturers called us and asked us to help port the methodology we used in semiconductor into battery. So in terms of challenges, Nika, to answer your question, I would like to extend on what Selena just mentioned. To me, the trade-off between the investment needed to see all the fail mode in the battery cell manufacturing was the profit margin, for cell manufacturing. That trade-off is challenging for everybody. Let me give you one like a benchmark data point. We worked with some of the leading cell manufacturers, large-scale cell manufacturers in Asia, and we work with them to build hypothesis trees to say, hey, here is a fishbone diagram for your fail mode. Then you look at, do you have all the sensors, all the inspections in the facility to see those fail mode? And it turns out roughly only 30% of the fail mode is observed in the facility, and more than 60%, there's no sensor or there's no inline inspection. And this is not only one facility, this is not only one, cell manufacturers, this happens at many places. It's not that, as Selena said, it's not that people don't know those fail modes need to be observed. It's that the cost of doing that investment and the priority associated with it, that is a challenge. Of course, people are exploring smarter ways to make that decision. One of the way, and there's many ways, one of the way is, can you use data to drive that decision, right? Connect the engineering decision with the financial decision. And can you, for example, use AI to make that decision smarter? And it is really a big challenge for manufacturing.
Thank you, Michael. And that helps us lead into our next little topic. So lessons from the semiconductor industry. So Michael, in the semiconductor industry, process control, quality control, yield management have been refined over decades. The battery industry is still catching up in some of these areas. So what role does analytics and inspection play in fabs? And what are the biggest lessons battery manufacturers can take from semiconductor fabs and how they operate?
Okay, battery manufacturing has its own challenge, right? And the industry has made tremendous progress from R&D to process. But if you look at, what's common between semiconductor industry and the battery industry, in terms of yield and the quality, which was the number one in the pool, I would say in general, there's a need for better monitor and inspection. And then there's a need for better semantic data model to align all the information you got. Then there's a need for better analytics. So if I break down a little bit, in terms of monitor and inspection, I think I mentioned earlier that, 30%, maybe you have that information only 30%. I reflect in the history in semiconductor, we all know in semiconductor, TSMC is the biggest, foundry. If we look at it back in about 20 years ago, nobody in semiconductor industry is doing fab-wide process control, install all the sensors in the equipment. And TSMC actually brought PDF in, we did a joint project, and we start to doing all the process controls on all the sensors on the equipment. That's how what in semiconductor is called FDC. I think in battery we call IoT. And that is how was started in semiconductor. At that time, frankly, TSMC does not know whether this thing is useful or not, but they have this belief and they made this investment. And the 20 years from that, look at it now, every semiconductor facility is doing that 100% and more. So that is the investment TSMC did. And similar things, I think, need to happen in battery space. So that is inspection. But once you have the inspection, then you got all the data. Then the next step is, how do you align with the data, right? One example is when we work with many battery cell manufacturers, the challenge is how do you align front stage process to the backstage, including testing. So for example, if you have a battery cell that failed, and do you know what is, for example, the mixing condition, what is even the humidity, the number of moisture in the air when you did the mixing, right? Do you have that? Even if you have that data, can you align the data? In semiconductor industry, there's a standard called E134 and E123. Those specifically talking about those things. In battery space, I think we as an industry should work together to come up with better standards to address those issues. Now, if you have the data, then the last thing is you got to do analytics that actually drive actions. I mean, there's a lot of applications, AI and otherwise, that we can use. but we need to combine the domain knowledge with, the data scientist to make the action, to take actions from those data. So to summarize, those are the three things I see from semiconductor industry. You need to be able to see the problem, right? So the question is about the investment. You need to be able to align with the information once you see the problem. I think the battery industry need to come up with better standards. And then third is you got to drive actions out of all the information.
Thank you, Michael. And that leads us into our next question. So you mentioned some differences and areas where the battery industry needs to improve. And one of those difficult areas is traceability. So of course, it's different than making a chip when you have an electrode then gets assembled into a cell. And many cell manufacturers are having different methods to deal with this, with calculations, but also etching QR codes on electrodes. So it just highlights how different battery can be. So Selena, I'd love to get your take on how do you think these lessons apply to battery manufacturing? And are there fundamental differences that make it harder to apply these lessons directly to cell production?
Sure. Okay. So, Semiconductor has done a huge amount in developing really great metrology and failure detection and so forth. And a lot of it can be applied in battery, but there's a couple of things that really set battery apart. Semiconductor and battery, both very high precision industries, all right? So, I know in semiconductor, you're looking sometimes in nanometers scale, but in batteries, you're looking in micron scales, right? The tolerances are kept within micron scales. The defects can be at micron scale or, just subtle chemical defects. But the thing with batteries is the speed is so high. The takt times are so high. And that's something that's really different between batteries and semiconductors that, your tolerances are teeny, but in batteries, your takt times are in microseconds in many cases, right? Cells will move on a production line faster than you can see, right? And the volumes of individual cells are so big. Now you can say, well, I could do big prismatics and slow everything down, but even those are going to be fast. If you're doing cylindrical, which is what, that's what's in most of the leading vehicles, you're making millions of cells a day. Okay. And that comes with some sets of unique problems. Just moving that much material through a factory means that your equipment is super beefy and it's going to have wear on it that you don't expect with stuff that's going slower. So, just the fact that you move, a couple million cans down an assembly line, even if it's a couple 100,000 cans a day, what happens is all those cans wear just a tiny little bit. And at the end of the day, if you, go run your finger over the fixtures and tooling, you see this slight sheen that you pick up of just very, very fine powder. That's going to be the result of the cans themselves wearing. And it's not like every can wears a lot. It's just a teeny tiny bit. And so what you'll see is the maintenance needs, and the dirt in a factory that's making cells at that kind of speed just goes up. It's never as clean as you think. The parts are also always wearing more than you think. And then when you send your maintenance team in, they're going in there looking more like auto mechanics than you actually might think. Because what do they have to deal with? They have to deal with tooling that is seized, right? Because it's gone through so many cycles and, lubricants and powders and other stuff. So it's a fundamentally, and not because people are lazy, just fundamentally because the amount of material you move, it's a dirtier environment. It's a faster environment. And that's where, yes, there's lots of things you can apply, but there's these realities as well.
Definitely. Thank you, Selena. And, you talked about it's a much dirtier environment. So that kind of leads us into the next topic of some of the challenges in electro production, with one of them being contamination because of the way battery manufacturing is. So Kenzo, I'd love to pass it over to you. So first, I'd love to get your opinion on what Selena and Michael mentioned, and then dive a little bit more into what are the common issues in electrode production that impact yield.
Yeah, I think Selena touched on the bulk of it is for example, in electrode production, if you're going 80 meters a minute at 1.2 meters wide, and you find a contamination that didn't come out until, let's say, formation and aging, you have to rely on, well, when did it happen and how did it happen and how much of my millions of cells does it affect? And that only exists, hopefully, in inspection data and traceability, which is super challenging. Like you said, on electrode, you tag it with a QR code somehow. And how do you scope that problem and how do you disposition that problem? Does that one particle that we found matter for the entire batch? Is it just a series of cells? And that's what happens sort of all the time in coding, where you get these bubbles or streaks or agglomerates, and you just don't know. Most of the time, you just don't know how much it affects and how much you should throw away and how much you can keep. So yeah, those are certainly the challenges sort of specific to battery manufacturing, I would say.
Yeah, and you don't have a lot of time to decide whether you're going to keep it, right? Because you
Mhm.
fundamentally don't have the space to store that, right? If you think about what the footprint looks like, oh shit, something bad happened. I got to store today's cell production while I sort out if it's good or bad. You don't physically have the room in the factory,
Yeah,
right?
sometimes the activity is let's store it for 5 more days, and like 5 more days of 5 million cells a day is, like you said, a ton of footprint.
Thank you, Kenzo and Selena. I think automation can be super helpful in making those decisions. So Hai Long, in Asia, there is more automation in coding processes. So what are the advancements you've seen and what challenges remain?
Yeah, so for example, for coding machine these days, it's pretty automated, from the unwinder to the coding subsystem and to the coding diehead and so basically, it's definitely getting more and more automated. And I've been seeing big improvement on those like motorized diehead where you can change you can draw change the shape of the diehead and the gap between the diehead and the substrate by through the feedback from the beta ray data and from the dimension data you're getting from CCD, right? So it tends to work pretty well for like if you are only making single type of battery, right? And maybe for a certain period of time, right? Like Selena Kenzo mentioned, like there's a lot of variation in the battery manufacturing space just because of the volume of the material you're going through. And very often you tend to multi-source too, which means you are getting the raw materials from different vendors. They may have slightly different furnace temperatures. So yeah, so there's definitely people are trying to get more automation done. But it's still there's still a big challenge when you have to switch between different cell models and when you have those seasonal fluctuation. And then I think that still needs some time to work on.
Definitely. And Selena, what are some exciting new technologies that you're looking at for Lyten, maybe some that Hai Long mentioned? And also I'd like to know, you've worked on, I think, 3 or more different chemistries, now working on lithium sulfur. So how do challenges in electrode and even cell manufacturing differ between these chemistries? And is visual inspection important and how is it applied?
Yeah, so visual inspection is always important. I don't care what chemistry you got, right? Because if you've got a gap in your electrode for whatever reason, whether it's a scratch or a bubble, that's going to cause problems for you. In some chemistries, it causes safety problems. In other chemistries, it just gives you bad performance and warranty problems. Doesn't matter. You're going to pay for all of them. So, that becomes an issue anywhere. Whenever you're doing slot die coating, right? And even if you're doing dry electrodes, in the end, the quality, the surface quality of the electrode, its density, and its just straight up appearance, it always matters, right? So this is something that it just transcends chemistries, right? The implications downstream might be a little different, but not that different. You know, if you have zones that have gotten way too much electrode and other zones that are starved for it, your cell performance is going to be poor. Doesn't matter which chemistry you've got, right? And then, you know, with all these chemistries too, when you talk about manufacturing, you are talking about speed and scale in every case. And so the things that Kenzo and Hailong mentioned, they're not, you know, unique to any one chemistry. They just shift depending on what you're running down your line.
Thank you. So let's get a bit deeper into one of our topics, which is AI. So I'd like to ask everyone in the room first on another poll, who thinks that AI will play a significant role in cell manufacturing in the near term? All right. Hopefully everyone's able to see the results live.
And I'm happy to share the results live, Nika, when we're done. Looks like 10% are sitting in the I don't know.
Yeah, it's a big area of unknown for sure. And it looks like everyone should see the results now, Myra, right? It looks like the most popular answer was yes, they'll have an impact, but challenging to see the use cases. So let's talk about use cases of AI and advanced analytics for cell manufacturing. Michael, I'd like to pass it over to you. So from the inspection standpoint, what's the next frontier for AI in battery manufacturing?
So I actually big believer in using optical for inspections and use AI to drive that. A lot of that, my belief, is driving from what I mentioned earlier, the trade-off between capital investment versus what you can get out of it. Of course, there's a lot of more advanced things like X-rays, ultrasounds, and all that stuff. But optical really, frankly, is the cheapest solution. But to get to optical work in large scale, you need basically all the AI applications to interpret what you see, right? There's low resolution optical, there's high resolution optical, but you really need AI to extract features out of what you see. And that's my belief is one of the very hot area.
And I think it's an exciting area, even outside of battery. You see so many image recognition algorithms coming out. A lot of them are open access and can be applied, you know, across industries. So it's definitely an exciting area. And I feel like, you know, every year you see new inspection technologies coming out. This year, optical is playing quite a large role, and everyone is starting to use AI to help process such a large amount of data. And I know Michael and I have talked about this before, but a lot of automotive companies require battery producers and semiconductor producers to keep a lot of the data. But when you have so many images coming off inspection equipment, how do you actually store those images? And a great AI pipeline can definitely help with that.
I do want to add one piece of good news is another, you know, benchmark data point. We were talking with one of the top cell manufacturers in Asia, and I was told they plan to increase their budget on inspection, you know, sensoring, including AI, up to more than 20% of the total capex.
Wow.
Which is tremendous if you consider in battery space. Of course, in semi space, it's like 33%, which is too much. But increasing that much to dedicated to inspection, especially AI-driven inspection, to me, is very exciting.
Yeah, definitely. And a lot of cell manufacturers are opening their own AI and data analytics departments. So Hai Long, I know you and Selena worked in Panasonic to scale cell production, and you've had plenty of experience seeing factories grow. So what role does or should analytics and AI play in cell production?
Yeah, so in general, like these days for the gigawatt hour size the factory, you pretty much need the data for all the decision making, right? From production delivery quantity to to quality management and to the traceability and even the inventory management. So getting all the data from the product and which is very important, and getting more and more data from the machine, from the sensors, and know how to utilize them, and together with the product, and to have the appropriate feedback is very important too. And also during the battery manufacturing process, there are like roughly probably 20 places where you can place the visual inspections, right? So that you for sure you're going to go through a lot of images, and especially during the electrode making process, like the web, sometimes it vibrates, and then sometimes it's going through really fast. You are not always getting a very clear picture, and having a good AI algorithm and the library to make appropriate judgments, so you can pass the good product through the downstream process is also very important for efficiency. So I think we're going to see more and more AI applications in the visual inspection. And also I would expect to see more AI on the predictive maintenance, but basically being able to really apply all the data together and make a good algorithm.
Thank you, Hai Long. And I'm personally interested to see how AI helps detect different fail modes early on in production, because I know in battery, a lot of the issues you see at the end of line and information and aging. So how can we speed up that process so we don't have to wait all the way to the end of line to actually find out, hey, there's something wrong with this batch of cells? So Selena, I'd love to get your perspective on this. How do you see all of this and AI impacting the scalability of Lyten's future gigafactories?
Yeah, so as Hai Long mentioned, with vision systems, AI is a natural, particularly with things like defect detection, because defects they look all different, right? You can use vision systems for doing things like tab placement, and is a insulator present or not present. That's very straightforward. But when you start looking at defects, it just gets harder, and you need something like an AI system. But I think the future is probably beyond just vision inspection. There's a lot of things that are linked in a factory, and even if you are relying on finding out what's going on at end of line, it's still helpful at that point to be looking at the data, right? To be looking at your formation data and seeing trends in this. It points you to things in line, and it requires quite a bit of analytic work to connect the data that you've got at end of line all the way back through the factory to where the source of the issue may be coming from. Takes good understanding from the engineers who understand the process, but it also just takes a lot of sheer work to go and say, okay, I've got some weird capacity numbers coming in at information. And, maybe they're all within spec, right? So if you're short on staff, you kind of look and you go, cells in spec, ship it, and that's it. And you don't think about it at all, right? But do you have that little bit of extra time to say, hey, I'm watching some trends, and I'm seeing some variability in my capacity numbers. Can I trace that back to specific things that are happening at coding? Can I take to certain regions of the coding? Can I take it back to certain winding machines? Can I take it back to electrolyte fill? where's this coming from, right? And every time you do that and you figure out what's causing your variation, you can tighten it down and you can produce with more confidence cells that are in spec, or you can tighten down your spec, and that gives you more, makes your cells even more valuable, right? So, trying to not just make cells that are defect free, but cells that you can ship at a higher price, right? Or you can say now, well, I'd like to increase my energy density. Am I going to be able to maintain the output because, am I going to have a tolerance stack up where, some significant fraction of my cells I've got to scrap because I'm going to have capacity issues in the future? Well, if I've figured out what was causing that variation, I say, oh, okay, I can control that better now. I can go tighter to tolerance, which gives me better throughput or a better product, right? So I think that's where there's a lot of gains to be made.
Thank you, Selena. And that makes me think of one of the biggest challenges in the battery industry is talent gap. Everyone is looking to find those engineers who worked on large production lines who can just put their hand on coding equipment and say exactly which parameter needs to be adjusted. And I think AI and analytics can help automate that process. So we're not relying on, this inherent talent, and, we're not prohibiting amazing talented engineers from entering the space, even if they don't have the experience in working in a gigafactory. I know, Kenzo, you talk about that a lot, so I'd love to get your insights on what has been discussed, and I'd love for you to close us off and give some parting thoughts, maybe one piece of advice to battery manufacturers looking to scale while maintaining high quality.
Yeah, I think of all the things that we've been talking about, I don't know if there's any one thing, but it boils down to maybe a little cliche, but to go faster, I think you should slow down. First is what I've sort of seen in industry is people trying to do too much all at once in parallel, from materials characterization to speccing out a gigafactory equipment, all the same people doing the same thing. And those are the mistakes sort of I think we're seeing being made at some of these companies that have been struggling. So yeah, I guess it would be slow down, take the time to do your materials development, process development, equipment specifications, specking out the right inspection, looking at your data, analyzing the data, and using that data to make decisions. So all sort of encompassing it to slow down. Then you can go fast. So. Yeah,
right. Thank you so much. Yeah, thank you. What an incredible panel. It's been a fantastic discussion. So thank you all for sharing your insights. In a couple of minutes, you will be answering questions from the audience, but I'd like to take a pause and do a product highlight. So I'd like to now welcome Peter Koska, Director of Battery Solutions from PDF, to present on advanced electrode inspection technologies and how AI is transforming inline manufacturing analytics, touching on some of the many topics we talked about during the panel. Peter, over to you.
Hey, thanks, Nika. Yeah, if you can go to the next slide. So, great. So the core idea here is how can we use AI and that power of big data to learn from one line to another line, and ideally we could learn from pilot to gigafactory, or from one line on a gigafactory to another line in a gigafactory. The challenge, of course, is in order to be able to use AI, you need a lot of access to very similar looking data. And when you're looking at industry data and even more specifically battery industry data, where the technology is changing so quickly, that's not so easy to do. So the approach that we took is, well, what if we zoom in? What if we zoom in at the micron level to images that look like this? Now, do the electrodes start looking similar from one product to another? And so we've worked with 8 different manufacturers now, and what we're finding is, yes, indeed, If you start taking images with 1 micron resolution or so, you start learning what a good electrode looks like. And we've built an entire system around this. So we now have an inline microscopy camera, which connects to Edge AI, and which is able to interpret the images real time and find the features that make electrodes that we expect to see in electrodes, and thereby identify the things that we don't want to see in electrodes. And so it's a fully scalable AI approach where you can learn from one line to another line and continue growing your knowledge. So I'm going to go over some examples here of where we've applied this at different sites and the results. So here you can see our AI finding each good grain, and it's drawing an outline around the contour. Again, this happens in real time on your production line. And in this set of images, we can see that the image on the left has fewer good grains. Fewer contours around grains, meaning fewer quality grains were found. If we do subsequent analysis on that, we see grain collapse due to over-calendaring. You can see that in the zoomed in images. The top image on the left has dark centers, which is a sign of grain collapse. But our software is able to find this difference in real time by looking at a difference in grain size distribution. So note the chart on the right, which again is generated in real time, shows a difference in grain size distribution and can be used to generate alarms or do some sort of process change steps in real time on your production line. This next example, so these images show impurities found in an electrode. The biggest one here is about 50 micrometers across and almost 10 micrometers out of plane. And again, our software can identify these, can identify the impurities, measure them, locate them, detect if they're out of plane. And just to highlight, the size of these is so small that any regular inspection system would miss all of these. So once you're capturing data from micro defects, if you want, you can combine that with macro defects from other systems. That's something that our software would allow you to do. And now you can learn how to identify the onset of the macro defects through the micro defect frequency. Ultimately, you'll be able to understand and control defect distribution through looking at these micro defects without having to scrap electrode. In this final example, so we're using our camera and AI before calendaring, right after coding, to identify these recurring surface texture variations. And what you see here would have been deleted by calendaring, right? So after calendaring, you wouldn't see these small height variations. But with the system mounted before calendaring, after coding, you're able to see these texture variations, which later on could lead to varying porosity, varying cracking, and ultimately in your product, they could manifest as variable internal resistance, or variable capacity within each batch of cells. So in order for us to develop the system, there were a number of challenges we had to overcome. As a lot of the speakers spoke about, there's a huge volume of data. So we had to develop Edge AI that uses GPUs, which are co-located next to the line so that we're not sending tons of data to the cloud. We had to understand model lifecycle management. Again, this issue of traceability applies not just to materials, but also to the models that you use for understanding materials. And then we applied a lot of these emerging and maybe not so emerging concepts in data management, Kubernetes and Kafka and Helm, so that the whole system is fully scalable and reliable from one line all the way up to an entire gigafactory. And finally, we've combined this with a product that we've developed for our semiconductor applications, which is our Model Ops package, which then allows you full model lifecycle management that keeps track of each model version. So each version of AI, what it was trained on, what the validation results and the test results for it were, and where it's currently deployed. We don't have a ton of time, so I think that's it for me.
All right.
Back to you, Nika.
Thank you very much, Peter. So before we head into questions for our panel and for Peter as well in his presentation, really quickly, I'd love for everyone to answer the final poll. Would you like to learn more about PDF's optical measurement module for electrode quality? And please specify whether it's for full-scale production, pilot line, or R&D. All right, and I will start going over the questions now. I saw some really interesting ones, so I'll give you guys time to answer and start off with the questions. So Kenzo, I think you would do great in answering this question. So Atif asks, let's see, I'm just gonna answer this live. Given the latent nature of certain battery defects, how can one detect them, with AI or without? These defects may manifest early on, but may not be detected during formation and only become apparent during cycling at the customer site. How would you address this challenge?
Well, I don't know if I have a good answer to that, but that's obviously a very tricky one. You definitely get escapes out of formation and aging of sort of late onset self-dischargers or problems or defects that you said don't manifest themselves until their cycle, like lithium plating or dendrite growth. The answer I don't really know, but I'm guessing those types of defects that I just mentioned exist in the structure of the cell or the electrode. So having deeper insights into whether it's visual or other data or information of the electrode, I think will probably help with that sort of discovery that's within the manufacturing side versus happening obviously in the market.
Thank you, Genzo. So a lot of questions I've also seen are finance related, some of them saying that, you know, the profit margins are very different between battery and semiconductor, and some people asking what is the range of resources that should be given to kind of a full, let's say, AI and analytics and inspection stack. So this is a question for all the panelists. What kind of investment should cell manufacturers expect? And I know it's a tough one. It's a tough one.
Well, I can say that I'll say this. A lot of times when people are tallying up the bill for a factory, right? They focus a lot on their CapEx because it's obvious, right? They go out and they say, okay, I need a coder and I need winders or stackers and I need, you know, formation room. A lot of times because it's sort of new in thinking, people are not writing the budget for their digital architecture, right? It just it slips people's minds because it's like, well, how much could that possibly be, right? And I think the first thing people do is they need to put the line items in for their digital architecture. And you know, sometimes a lot of times this is hidden because, you know, the sensors will come as part of the tool or, you know, it's part of the process, but then the concept of, okay, well then I actually need to have these systems And, you know, people know, well, maybe I have to have a SCADA system or an MES system, or I'm going to, you know, look at my cell cycling data, you know, and okay, maybe, you know, maybe the Voltaic guys will come and they'll give me a budget for, you know, how much they want to look at cycling data and other stuff. But, you know, putting that together, recognizing the scale of it, and recognizing just how much data you're going to have, and, you know, the number of servers you're going to need, and the considerations for storage, it's new to a lot of calculations. But putting in the line items and having the discussion is the way to start looking at that number. As I said, everyone's going to be, you know, trying to trim things down, but you do have to consider what that means for your OpEx going into the future, and realizing that if you've got to have lots and lots of people running around the factory fixing things, that because you've got, you know, a line down, that's going to cost you a lot more, right? So hard to say, you know, directly for any given thing, but I think people need to start budgeting for it or planning it.
Yeah, I definitely agree with that. There are probably three components to run a mass production facility. You need roughly like 40 different type of softwares. You need your MES, you need your recipe management system, you need your defect management system, you probably want to do a SAP and all that stuff. So that's one category of all the software part of it. And there is a category of all the hardwares related to inspection, sensors. Some of them, as Selena said, come with equipment. Some of them you need to buy as upgrade, or you need to get by separate inspection tools. Then you have to consider all the again, very interestingly, many times company did not budget for it, which is the people to do all those things, the digital twins, right? So don't think about you can have IT of 3 people, you know, then you can run the fab facility. That's not going to happen. You need, you know, talking about significant number of, you know, IT, data scientists, and methodology people to make all those things work together. If you put all those together, I see numbers as high as 20%, which is, I know it's very high compared with the profit margin, you know, we see in the battery. But, you know, most of people just cut the cost and go way below that. And then they run into trouble when they scale up the production. Yeah, it's a challenge.
Great. Thank you, Michael and Selena.
And there are some strategy you can take, right? So yeah, I you know, it's always a balance, like, you know, having the full capability of managing everything versus, you know, having none, right? So but you know, it's a balanced decision when you invest on the capex. So, you know, the usual strategy I've been taking is maybe design the space in when you design the equipment, but don't necessarily buy all the metrology, right? Inline metrology. But later, once you start to run the production line, you see all kinds of problems. Now it's an easier sale to say, hey, I need this kind of tool, I need that kind of tool, and this is my ROI. And usually, you know, it can get pretty convincing from that way too. But the good strategy is to have the enough space designed in the machine in the first place, if you don't want to spend all the money in the beginning.
Very good point. Thank you. So now we have a few very specific questions and technical questions. So let's see if we can hit some of these. First one, is there any solution for identifying the welding dents on the cell surface area? Is it optical? Is it X-ray? How do we find the dents? Is it done at the end of line?
I guess, you know, you can look at welds as you make them, right? If you're talking like electrode tab welds, right? Usually you'll put a vision system there to take a look for welding defects generally. You can use, welds are usually pretty big, right? So X-ray inspection tends to be pretty good for this because you can get the resolution, you can see this stuff, right? So that one tends to be, pretty straightforward to do with traditional vision or X-ray systems.
Thank you. The next question is regarding process control. So the question is, what kind of correctables exist in process tools to correct for process deviations? And is it important to connect inspection to these correctables?
Yeah, that is basically the concept of run-to-run control, right? So you can feed forward, you can feed backwards. The challenge is how do you do a run-to-run control that is stable across different product, before PM, put maintenance and after maintenance between different tools. So you got to have a stable run-to-run control models. Once you have that, yes, and the people does implement this in the production line.
Any comments from anyone else? All right, next question. Is it cheaper to scrap early based on AI-assisted defect detection rather than wait and follow quote unquote, get the battery made for our metrics approach from Derek?
That's the question every production operations manufacturing leader asks themselves multiple times a day, okay? You start seeing some defects occurring and you're like, okay, we're scrapping. But sometimes something weird happens and, the like if you have something that sets everything off the rails, suddenly everything's scrap and you're like, what? Okay. At which point, I mean, you don't just say, oh, I'm just going to scrap and move on. You got to get in there and figure out really fast, is this real? Is this a spurious signal? I mean, lots of things happen in a cell factory that change stuff, right? And sometimes it's like, wait, what happened? Did I have some kind of power surge or something that really threw off all my equipment? Did something fall out of calibration? Is it real? That's what your entire manufacturing team is spending their day doing. You've got a big quality team, and then the factory leader has to decide, how much risk am I taking, right? Am I going to send this thing out, and is this going to be a huge warranty return? And, is this going to cost me millions of dollars, billions of dollars if I ship these cells out? What's my risk? What's the risk profile? And that's where you really have to understand what your customer's doing with their cells, what the implications are of a particular problem. I mean, it's one thing to be like, well, my cells are a little low on capacity. Okay, I can't sell them for as much, or the customer will be like, well, how come these cells are a little low on capacity? It's another thing of, oh, I've just shipped a bunch of defects and caused people's, battery systems to catch fire. I mean, it's a whole different risk profile. And you have to ask that question every day.
Yeah, I second to that. It's easier to say I'm going to bin different cells because of the different capacity I can sell at a different price. That's difficult decision, but it's relatively easy decision. It's much more difficult decision is, what does that mean for my quality, for my reliability? Is the cell going to catch fire, 3 years down the road? That is a much more difficult decision. I would also bring in the second aspect that I see people start doing, which is if you have a ERP system, for example, SAP, right, S/4HANA, then you can start to connect. We see people connect the engineering data with the financial and the operation data so that you can actually use some kind of data-driven analysis, basically to make decisions as, if I scrap this much at this stage, that means it costs me that much down the road, because I have to restart another row in order to make this order for customer, was my cost of continue doing this. So if people start to connect the engineering database, which we call the shop floor, with the financial database, which we call the top floor, and you can make financial-driven decisions based on the data. I start to see people doing that in the facilities, and it's give you another piece of information to help make that difficult decision.
Thanks, Michael. And so I know you were unmuted. Anything you'd like to add to this one?
Yeah, I was just going to echo what Selena was saying. The quality people in a factory, which I was at some point, have this way of understanding sort of the precedences, what that happened in a factory versus a new cell manufacturer. It has to be, or they tend to say it's black or white. So you just scrap because I don't know if this is going to affect my customer or not. Versus a legacy cell manufacturer, they have the history of, no, I think if we just make those cells, test for this one thing, we're okay to ship. And that library is what, so this gray zone that these legacy cell manufacturers have, they can lean on to disposition, because the last thing you want to do is obviously scrap the cells. So, yeah.
Great. Thanks, Genzo. I have an AI specific question for Peter. So what is the level of training and machine learning required, for example, for optical electrode inspection? And how important is it to have robust data at the finished cell validation testing, cycling, and other aging effects, for example, to understand the correlation of a given defect type versus functional effect on actual cell performance?
Long one, good one. So
one.
the first part's relatively easy. If you're using something at the micron level, then the amount of training is fairly minimal, at least in our experience. These electrodes tend to look fairly similar. So, for example, the models that we offer would work almost out of the box. If you're looking at macro scale defects, then those will be fairly unique for each line. More training would be needed. Not exactly sure how much. As to the second question, I think maybe some of the other panelists might have a better opinion on this. Obviously, it would be fantastic to tie the optical data to your performance, but it is fairly expensive. And some of the things that you'll catch as defects as optical defects might not show up until quite late in the cell's life. So yeah, it'd be wonderful to capture that data in cell performance and build the correlations, but it might be very, very difficult in some cases.
Great. Yeah, thank you, Peter. We have a question about what are the challenges in scaling from pilot line to manufacturing line?
Well, that's just a big question, isn't it?
It's pretty big.
Like it's just, it's so hard. I mean, every part of cell making is challenging, and you're going to run into all kinds of questions and issues. Stuff you make on a pilot line, you're going slower. Just the fact that you're going slower means that you don't see a lot of the potential problems. You have to. You run into things where a process at one speed is very different than a process at another. In just aerodynamics changes. Are you moving electrode? And how long it alluded to this? Is your web vibrating? Right? What does that do? How does that affect what's happening? If you're winding cells and you're suddenly going faster, all that electrode is moving faster now. Is it bouncing out of position? All these things come up. I think that the best advice I can give people is work with good equipment makers. They have a lot of experience. they've seen it before. And as Kenzo alluded to, there's this legacy understanding, right? And take people's advice. These guys who've been making this equipment for decades, they haven't just made equipment and thrown it over a wall, right? They've made equipment. Their customers have had problems. They've had to go in to the customer site, look at this equipment, look at the problem, help the customer work through the problem. And then, they keep iterating their equipment to make things better. It's really good idea and cost effective to take their advice. Like, ask for it, because they know a lot of stuff that you're trying to scale something up, and they're thinking, oh, I've seen this before, right? They're like, oh, here we go, right? We're gonna have this problem, this problem, this problem. That's how we should address it. It helps you a lot if you listen to them.
Mhm. Great. Thank you, Selena. There's a PDF specific question. So Michael, perhaps over to you. So can PDF share a case study where there was a solution implemented in a gigafactory and what was the outcome? Can you share the benefits that can be achieved in terms of yield, scrap, etc.? Quantify if possible.
Okay, obviously we cannot disclose client-specific information. I can talk about in general what we deployed. So in one of the example, what we deployed is we deployed end-to-end analytics. So what does that mean is you take all the informations that the customer try to observe in the production line, right? From the front stage, from the mixing all the way to the backstage to the measurement. And then if client missing certain informations, may that be missing sensors or may that be missing some inspections, we work with vendors or even use our own OEMs to fill up those missing areas. Then gets to a question, I think one of the panelists mentioned early, hey, how do you decide to put all those information in? It costs so much. So one of the use cases we did is we take 1/6 of the line, gigafactory has many, many lines, right? So we take 1/6 of it, we implement as much as the budget allows, then we use that to do data analysis and drive what are the high priorities, and then the facility implemented to the remaining 5/6 of the line. So once you have, that's the first layer, you try to see all as much information as possible. Then you get to the second layer, which take 6 to 9 months to make all the data alignment correct, because each different equipment have different requirement to do different alignment, and sometimes you actually don't have the information, right? So for example, you do anode and the cathode thickness measurement is going through a foil which is moving at 1 meter per second, right? How do you know that the thickness measurement is associated with that battery cell? There are cost more expensive way by printing various things. The cheaper but less accurate way, because location equals speed times time. Speed you can get from the sensor of the roller, right? Moving. Time you have it from the MES system. You can calculate it that way. But it takes 6 to 9 months to make all the data alignment work. Then from there, then you can build all kinds of applications on top of it. Could be as simple as process control, set up control limit and do alarms, or could be as complicated as run-to-run controls. So one with example, I can give you one, for example, because it's asking for quantitative thing, right? So one of the example I can give you is we implement one of the run-to-run control modules, which reduced their excursion rate by 2/3. So you can calculate, I cannot tell you exactly what is the excursion rate because that's confidential information, but it does work. So those are the things that it works. So it's a lot of effort. It takes actually belief that this thing will work, and it will go through all the pains of 9 to 12 months. There's no return of investment, but you just have to believe it and then go through it, and eventually you get to the promised land. And it's going to be continued work.
Great, thank you, Michael. And I know we're very over time, so maybe we can close with these set of questions. I really appreciate the panelists staying to answer all of your amazing questions. So a little bit technical. Are there limits for continuous monitoring, web speed, computing power sizing, and width? So I think Peter, perhaps, or Michael can answer that. And then kind of on a similar wavelength for all the panelists, are there established ways of determining return on investment for inspection system investments? So let's start with the limits for continuous monitoring.
Sure, I can try that.
Yeah.
No, but it costs a lot of money. So I think what you'll find is the more data you want to process, it costs you more in sensors and it costs you more in compute power. At some point, there's diminishing returns. But I think if you crunch the numbers, you'll realize that in order to have part per billion inspection, really isn't that difficult. So I think if you start thinking of your inspection process in terms of what is, what's the inspection level that I'm willing to tolerate? Is it PPM? Is it PPB? Is it PPT? And then you can scale your inspection equipment based on that, then anything is possible.
Right. So we have, just add to what Peter said, what some of the deployment that we have, there's many terabytes of data per day. And if you just save all of those, you can, but it's like extremely costly. And if you want to save it for 10 years, so you got to use applications like AIs to decide what you want to keep, what you don't want to keep, and still satisfy the reliability requirement, right? So, for example, for our OEM machines, we do AI on the edge. So we only save the image that we believe has an issue. For the 99.9% of the image are there, they should be good, right? So the AI decide I'm only going to save 1 out of 1,000 or 1 out of 10,000. That's one way to save, to get your cost down. So you have to build into your design that how do you make that trade-off between information and the cost.
And sometimes it's just enough, you don't need 100% inspection. It's enough to know that, hey, there is more contamination on this batch of electrode. We should look into it instead of saying this is exactly how many, copper particles there are on this electrode. All right, and to close us off, panelists, how do you determine ROI when purchasing an inspection system? It's a tough one.
I have a cheeky kind of answer. Like, I don't know if there's an ROI, but I think as a cell manufacturer, you're going to have a field return at some point in your existence. And if that field return, causes, millions of dollars in penalties or losses, I mean, you wish you had that inspection system that caught that burr or that, defect, or whatever it is that is the root cause of that field return. But know that I don't know a cell manufacturer that's never had a field return or a problem with like a burnt cell somewhere. So yeah, I don't know if there's a metric ROI, but I think it's a sound investment, and I would do it if I was running a factory.
Yeah, I would say that there's no one way to determine ROI. I say this is where you got to hire good engineers. And people sometimes think, oh, I'm going to have this lights out factory and it's going to be easy and we're just going to do this. And it's going to be, no, you got to have really good engineers because every project is going to have different implications. And you need those guys to take a look and say, okay, this is what this inspection system is going to cost. Here is what it's going to actually produce for me, and here's where I'm going to recoup that cost. And is it a, am I recouping this in a year, in 6 months, in 3 years? What's that look like? What are the risks that I'm trying to mitigate? To get to Kenzo's point, if this is a big risk and the cost is going to be huge, that's one thing. And if it's a minor risk and the cost is going to be modest, that's another. But this is what engineers do, right? So how do you determine ROI? You get good engineering staff that will actually look at this and do a detailed and deep analysis, and not just be like, oh, I'm going to buy this tool and it's going to be great. They got to buy the tool. You got to think about installing it. You got to think about maintaining it. That's all the costs that are going to go in. What are the scraps? What's going to be the false positives, false negatives? All this stuff goes into that proper analysis. And, if your engineers are good, you're going to have good results.
Right.
And this is actually a great thing for you to do during the pilot process, right? So you're gonna basically, during your pilot run, you're gonna start to see all kinds of issues related to the new cell design, right? So one of the key element for to scale up is to have in the DFM document you have the PFEMA, right? So in the PFEMA, based on your pilot trial, you can you may be able to guess, okay, what kind of potential failures I may have, and if I have this kind of inspection tools, and how can that help me reduce the risk later on. So that's one strategy. And otherwise, like you just have to see, right, during the production, like when you start to have all these different losses, Kenzo and Selena mentioned, then you have a way to calculate this. But the bottom line is to know what problems you are solving, and know what kind of technologies to use, and to whether it can be effective or not.
Thank you so much. And thank you, panelists, for staying over time. We have so many questions, a lot of them very technical and interesting. So for those whose questions didn't get answered, you can feel free to reach out to me with those questions, and I'll see if our amazing panelists can answer those offline. So thank you, everyone, for coming. We really appreciate your time. I hope that you learned something new. And thank you very much, our incredible panelists and presenters, for providing this insights on such an interesting topic. Have a great day, everyone.
Thanks, everyone.
Thank you.
Thank you.
Bye.
All right.